Okay. Is the screen visible now?
Yes, sir.
Yes, sir.
Okay. So today we will see the truss problem once again, but this time we will see the how to give the inclined roller support. This was already covered at your theory class. So here I have a very simple problem with me. This is different than the problem which is covered in the theory class. So everybody can do this. It's a very simple one. So it's a simple truss, and here you can see it is having three members. Let us say this is member number 1, member number 2, and member number 3. All these members, they are having same modulus of elasticity and same cross section area. The modulus of elasticity is 200 kilonewtons per mm square, and area is 50 by 50 millimeters. So the length of this particular truss, so the horizontal distance is 1, so the length of this member is 1, and the length of this vertical member is also 1. So definitely the length of this diagonal will be something like 1.414. Okay. Here this truss is getting support by a hinge support at this bottom, and there is a roller support at this joint, and there is an inclined roller support over here. So now see this length, this horizontal distance is 1 meter. So this distance will be also 1 meter. So definitely the angle which is made by this particular member with the horizontal axis will be 45 degree. And naturally, because of that, this roller is also having an inclination of 45 degree with the horizontal axis. So the modeling of this particular truss is very much similar to the modeling of truss which we have seen in the earlier class. So let us try and model the same thing in the SAP. So I have this SAP ready with me. So at the bottom, you can see there are units. So units right now, they are defined as kilonewtons and millimeters. And fortunately, we have everything in kilonewtons and millimeters. Okay. So let me create a new file. So when I create a new file, so I'll be working in the x-axis as well as in the z-axis. So the distances in the x-axis is 1 meter and vertical is also 1 meter. So I'll be needing only one grid space. So in the x direction, there is only one grid space is required. In the z direction, there is only one grid space required. In the z direction, no grid space is required. As far as the grid spacing is concerned, we can have 1 meter each, because if you see the problem, the distance between these two grid lines, they will be 1 meter. So 1 meter is nothing but 1000 millimeters. So here we have already defined the units as millimeters. So here I am going for 1000. Here also I am going for 1000. So here you can see my truss grid is ready. So I am shifting the mode to x and z plane. Okay. So if I move your cursor over here, you can see the coordinates over here. Okay. So here you can see the coordinate is something like minus 500 millimeter in x-axis, and here this is plus 500 millimeters in x-axis. If you click over here, so you will find the y coordinate is 999.3. So this is almost 1 meter. Okay. So let us start defining the problem. I'll go to the define. I'll go for the material. Okay. So as far as the problem is concerned, the modulus of elasticity is 200 kilonewtons per millimeter square. Okay, so let me select the steel. I'm going for modify the steel. So in the steel itself, you'll find the value is 200 and the unit is kilonewtons and mm. So this value is okay. So if you want, you can change this value if the different value is given in the numerical. So I'm not going to change this. Then we have a frame section. Okay, so as far as this frame sections are concerned, we have a frame section which is having the cross section area as 50 by 50 millimeters. So here the older cross section which is already available, I'm going to modify this. Let us call this as FACT1, that is frame section 1, and this will be definitely made up of steel, and this will be 50 by 50. Okay, so this is okay. Then the most important part, that is the static load case. Okay, so remember here you have to reduce the self-weight to 0. So that's why the self-weight multiplier factor should be set to 0. Then you don't have to press OK. First you change the load. Okay, this is a very common mistake. You change the load. As soon as you change the load, you will find this 1 will be converted to 0. So I'm pressing this key now. So you can see this has been converted to 0, and then you press OK. Okay, so now this part is done. So let me save the file. uh, Let us say this is expt3. It should not be blank space. So this is experiment number 3. So right now I have defined the material, frame section and the static load case. So now I have to go for the drawing. Okay, so drawing, so I'll be drawing a simple triangle over here. So I'm starting from this point, I'm ending over here, here and here, and then just say right click. Okay, so now you'll find this is exactly same as the problem statement. So now we have this member. This member is having height of 1 meter. This member is also having a length of 1 meter each. Okay, so now coming to the support. So we have a hinge support over here. So I'm selecting this joint and here I'm going for the hinge support. Okay, then if you refer the problem statement, here is a roller and here also there is a roller. So I'm selecting both the joints. Okay, and then I'm going for the roller support. Okay, so now you see both the joints has been assigned a roller support, but here you see the roller is horizontal roller, but in the actual problem you will find the roller is inclined roller and the roller has to be inclined by an angle of 45 degree. Okay, so what you have to do is here the rotation is always taken in the clockwise direction. So I'm selecting this particular joint and then I'm going for assign, then joint. In the joint we are going for the last option, that is the local axis. So here you will find the rotation option is there. So now this joint has to be rotated about the y-axis. Okay, so about the y-axis means perpendicular to the screen. So about the y-axis you have to rotate it by, say, for example 45 degree. Okay, if I changes this to 45 degree, it will not going to solve my purpose, because you see the roller has been rotated in the wrong direction. Okay, so it has to be rotated in the negative 45 degree. Okay, so here I am selecting this once again. I am going for assign, I am going for joint, I am going for the local axis. So initially I have given this as 45. Now I'll go for minus 45. So if I go with minus 45, you will find the roller has been oriented in the correct direction, which is there in the problem statement. Okay, have you understood this? Any questions? Okay, all you have to do is select the joint. Okay, go to the assign joint, and here you have to go for the local axis. If you want, you can give any angle, maybe 90 degree. For example, if you want a vertical roller over here, so you can select this joint, you can go for assign joint and say local axis. Here I am going for, let us say, 90 degree, for example. Okay, so if I go for 90 degree, you will find the roller has been changed to 90 degree. Unfortunately, both the joints were selected. That's why it is it is changed for the both the joints. Okay, so now I'm undoing this. So now you see the roller supports and the hinge supports are in place, in a proper place. Now what is remaining is the load. So at this joint we have a load of 100 kilonewton. So I'm selecting this particular joint and then I'm applying a horizontal load. So horizontal load is the global x-axis. So horizontal load of 100 kilonewton is acting now in this particular direction. So my problem statement is ready. I have given material. Okay, I have defined material, I have defined frame section, I have removed the self weight, I have drawn the geometry, I have given the support, as well as I have given the load. Now what is remaining is the analysis. Before analysis, you have to go for set option. So set option, we have to select the truss. Now this is a space truss. So space truss will have the available degree of freedom in x direction, y direction, as well as in z direction. But this is a 2D truss. So 2D truss is having the deformation only possible in x direction as well as in z direction. So I'm removing the uy. Okay, so you will have only deformation in uz and ux. So I'm saying okay. I'm saving the file once again. I'm going for analysis and say run analysis. So you see my analysis is complete because the entire thing was the input was quite correct. So now if you see the animation over here, okay, so I'm starting the animation. So here you can see the roller is perfectly working. So this particular roller is getting rolled over a inclined surface of 45 degree. As far as this roller is concerned, so this roller is perfectly moving in the horizontal direction. Okay, so the displacement in vertical direction is restrained, and here the displacement in the perpendicular direction is also restrained. So this is how the inclined support has to be given in the SAP. Now if you want to see the output files, so what you can do is you can let us first of all see the joints reactions. So here you can see the joint reaction. So here you see the reaction is perfectly perpendicular to the inclined support. Here also the forces are there. Okay, so these are the joint reactions. If you want, you can see the member forces. So axial forces, auto, then we have to show the values. So you can see all the values are there. So you can see that this particular member will be subjected to tension. So this tension value is 70.29. It is reflected on the screen. And if you want to see the nodal displacements, we can go to the file. We can say print output table. So in the print output table, if you want, you can print the reactions as well. Okay, frame forces also you can see, and you can print this into a file. Okay, so I'm printing this file into a folder called as C SAP experiment3.txt. I'm saying OK. So once I click OK, a file is created in that particular folder. So here you can see my location is C SAP, and this is my experiment number 3 file. Okay, this is the latest file which is created. So once I open this particular file, you will find the results. So these are the joint displacement. So remember, when I have drawn this was my first joint, this was my second joint, and this was my third joint. Okay, so when I go for the first joint, so here you will find the first joint, it is not having any joint displacement, because here you see the first joint is your fixed. The second joint is this one. So second joint is having a displacement in the x direction as 0.1988, and the units will be millimeters, because here you can see there is millimeters written over here. So this is 0.1988 in the x direction. Now this is which x direction? This is the x direction which we have defined. Okay, so this particular joint is moving in this particular direction, that is in the inclined direction. So in the inclined direction, that is in the 45-degree angle, you will have a displacement of 0.1988 millimeters. So here, if you want to find out the equivalent displacement in the global axis, so here you will have a displacement vector of 0.1988. So we can take a 45-degree component of the displacement and 45-degree component of the displacement in the vertical direction. So this point will be moving in this global x-axis by a magnitude of 0.1988 into cos of 45. Okay, so this is going to give you the dx, that is x in the global axis. And if you want to find out how much is the y, so you have to do is just 0.1988 into sine of 45, because the angle is 45. So in this way, this point is moving in x direction as well as in the y direction by the same amount. Okay, because the angle is 45 degree, and this way you can get the displacement in the global x-axis. Okay, now as far as the third joint is concerned, third joint is basically restrained to move in the global z-axis. It is allowed to move only in the global x-axis. So third joint, you will see third joint is getting displaced by an amount of 0.3397 millimeters. Okay, so this is moving in the x direction. Okay, as far as the reactions are concerned, the first joint is a hinge joint, so you will get the force in x direction as well as force in z direction. The second joint is inclined roller, so this is what you are getting. So this value is nothing but your vertical reaction value in the perpendicular direction to the roller support. So this direction you will have a magnitude of 70.57. So this also we have seen earlier also. Let me show it once again. Okay, so this is 70.54, and this is 50, and this is 50. Okay, so this is 50, this is also almost 50. Okay, and lastly we have a very negligible reaction in the vertical direction for support number 3. So this is 0.17. Okay, so in this way you have to analyze the inclined support problem. You can have the member forces also. You can see the member forces, they are constant. So this is the actual forces P. You just have to refer this P. As far as the third member is concerned, there is a negligible force. Okay, it is 0. As far as the other portions are concerned, you can see the values over here. Okay, so this is how the support or the inclined support has to be given in the SAP. Okay, so I hope you have understood this. Any questions as far as this part is concerned? Please let me know. Okay.